here we have to calculate the magnetic moment of Cerium. Okay, so first it's very important to know the valence shell in which the unpaired electrons is present. For that we must know the electronic configurations of Cerium. So dear students, here first of all we have to see the electronic configuration. We have to see the electronic configuration of Cerium 3+ ion. Atomic number of Cerium is 58. So electronic configurations, you know that then Cerium having electronic configurations, that is xenon 54, then 4f, then 5d and 6s. These are the valence shell for Cerium. So you know that in 5 that is 54, so 1 electron D and 2 electrons in S2. So this is electronic configuration of Cerium. But Cerium is in +3 oxidation state, right? Here we are observing +3 oxidation state. Its electronic configurations is likewise. So you have this xenon 54. So what it means by +3? It loses 3 electrons from the valence shell. Okay, so this is a 6 and 5d are the valence, and these 5d and 6s electrons are lost. These 3 electrons are lost by Cerium and results into the 3+ ion. So its electronic configurations will be 4f1, 5d0 and 6s0. So dear students, this D subcell, D 5d and 6s loses the electrons and Cerium becomes +3 ions. Okay, now we know that Cerium has only one unpaired electrons in its valence shell, that is in 4f subcell. So this 4f having only one electrons, and due to this one electron, this Cerium shows a magnetic moment. So first we must know the value of Z. So Z, which is equal to, what is the formula? Z into Z plus 1 plus S into S plus 1 minus L into L plus 1 divided by 2Z into Z plus 1. So dear students, now as we have to calculate the value of J, that is either its value is L minus S and L plus S. So dear students, let's see this F subcell. I will try to draw here this F subcell, that is 4F. We know that this 4F subcell have how many orbitals? 7 orbitals. 1, 2, 3, 4, 5, 6 and 7. So these are the 7 orbitals, right, for F subcell. So this is a 3 plus 2 plus 1, 0, minus 1, minus 2 and minus 3. What are these? These are the azimuthal quantum numbers, that is a small l, right? And this capital L is the total magnetic moment, that is the summation of small l. What is means by this capital L? That is the summations of small l. So dear students, whenever we have, as this Cerium have only 1 electrons, right? So due to this 1 electron, this Cerium shows a magnetic moment. So this is only 1 electron which is responsible. For that, L value will be is equal to, what is the L value for this electron is, yes, you are observing, that is a +3. So dear students, therefore L is equal to, you will get 3. Now we have to calculate the S. So what is S? S is equal to total spin of electron. So how to calculate the total spin of electron? That is number of unpaired electron divided by 2. Number of unpaired electron divided by 2, which is equal to how many number of electron? Only 1 divided by 2. Therefore S, that is a total spin of the electron, is 1 by 2. So you got the value of L and S. Now we have to calculate the value of J. So their values are 2. Either one is L minus S and another one is L plus S. So which value we have to take? So see carefully, when the subcell is less than half full, okay, then we have to take L minus S. So see there students, 4F is having 5 orbitals and 7 orbitals, and these 7 orbitals have only 1 electron. So all other are empty orbitals. Okay, so means it is a less than half full. Half means this orbital is having the capacity of 2 electrons, but here it has only 1 electron. So one electrons, when we fill up on these 7 orbitals, then it becomes a half full, right? So it is a less than half full now, as it has only 1 electron. Hence, which value we are going to take then? We have to take L minus S. Hence, we are taking here the value L minus S. So what is the value of L? Is 3. What is the value of S? That is minus 1 by 2. So when we find out its value, so it becomes your 5 by 2. Okay. So dear students, therefore we get the value of J, which is equal to 5 by 2. Now after moving the value of L, S and J, we have to simply put these values into the Lanthanides constant that we have to calculate. So what is our formula? G is equal to J into J plus 1 plus S into S plus 1 minus L into L plus 1 whole divided by 2J into J plus 1. Right? So put the values of all these constants that we obtain. For J, what is, we have the value 5 by 2, right, into 5 by 2 plus 1 plus, what is the value of S? S we have 1 by 2 into 1 by 2 plus 1 minus, what is the value of L? L value is your 3 into 3 plus 1, right? So divided by 2 into, what is the value of J? That is 5 by 2 into 5 by 2 plus 1. If we simplify these equations, then we have to take this here 1 plus, sorry, this formula for G is 1 plus, so here 1 is remain to add. Now we have to simply this one later on we have to add, that is remain as it is. First of all, we have to solve this whole square bracket, right? So 1 plus, so after we have to solve this bracket first of all. Okay, so we will get very simple, that is 5 by 2 as it is. If we solve this first bracket, then we got it is 7 by 2 plus 1 by 2 into 3 by 2 minus, what is 3 into 3 plus 1 4 and 4 into 3, that is your 12, divided by, whole divided by, so 2 to get cancelled, and here 5 into, what do you have, that is 7 by 2, right, when we simplified it. Now in the next we have to very simply simplify this, solve this. After solving, we get the value near about 0.86. So dear students, we get the value of Z, that is 0.86. Now we have to put the value of this G into the equations here. So what we obtain, our Z value is 0.86. Okay, so very simply we have to put this value of G there, that is 0.86. Now into, we have to put the value of J. What is the value of J? Root of 5 by 2 into 5 by 2 plus 1, right? So which is equal to 0.86. So we already simplified it earlier, 8.75. Kept as it is 0.86. We have to take the square root of 8.75, 2.958. And when we multiply the 0.86 into 2.958, we get the value 2.54 bm, that is Bohr magneton, and this is your magnetic